Welcome to our continuing discussion of convection dominated flows. In the last lecture we were looking at the Taylor dispersion problem, okay, which is basically relates to the axial dispersion in a pipe. In a pipe flow you have a velocity profile that is a parabolic velocity profile. Okay. Velocity profile is a parabolic velocity profile. It is 0 at the walls and it is a maximum at the center, okay, and I have given you the form of the velocity profile in terms of the average velocity. If you introduced a plug in here, okay, that plug is going to get distorted due to the velocity profile, because the velocity is 0 at the wall and it is maximum at the center. So, it is going to spread something like this. Okay. Once it spreads, there is also radial diffusion. Okay. If the plug had not spread like I have in this problem, okay, it would just diffuse in the axial direction. Okay. It would diffuse from a shape that looks like this to a shape that looks like this. On the other hand, if it just does get distorted due to the mean velocity, it is going to spread in the radial direction as well, okay, and that spreading in the radial direction could enhance the dispersion in the axial direction, and it is that enhancement of the dispersion in the axial direction that we are interested in looking at. So, in the mass balance equation, we had included convection in the streamwise direction, diffusion in the cross stream direction. We had neglected diffusion in the streamwise direction in comparison to diffusion in the cross stream direction. This of course assumes that the length scale in the streamwise direction is much larger than in the cross stream direction. So, the gradients in the streamwise direction are much smaller. Okay. We will come back and check whether that condition is valid or under what case conditions it is valid. Okay. So, I just taken a moving reference frame, moving with the mean velocity of the fluid, okay, expressed the concentration equation in terms of that moving reference frame, okay, and got an equation which contains the axial convection and the radial diffusion, okay, and the parameter here was r square u by d, okay, where u was the average velocity. Now, the velocity was separated out into two parts. One is a part that is the average velocity in the radially averaged velocity. Okay. The radially averaged velocity is the average over the cross section. Okay. So, C was written as is equal to C bar, which is only a function of x, plus C prime, which is a function of r and x. Okay. C bar was given by the radial average. Okay. C bar was given by the radial average, okay, the average concentration in the radial direction, okay, which means that the average of C prime has to be 0. Okay. This is the deviation from the average concentration. Okay. C prime is the deviation from the cross sectional average concentration. Therefore, the cross sectional average of C prime has to be 0. So, therefore, I have written C of x r star, okay, let me write this as okay, with the stipulation that the average 2 integral 0 to 1 that is the average. Okay. That implies that 2 integral 0 to 1 of prime C prime has to be equal to 0. Okay. The second approximation we are going to make is that C prime is much smaller than C bar. Okay. That is, the deviations from the average concentration are small compared to the average concentration itself. That I will come back and check what is the accuracy of that, okay, in the next after we complete the solution. Okay. So, my equation was u into 1 minus 2 r star square partial by partial x of C bar plus C prime. Okay. That was the convection part, partial C by partial x, and I have written it as two parts, C bar and C prime. Okay. and here I had r square u by d, okay, is equal to 1 by r star d by d r star of r star partial of c bar plus c prime by partial r. Okay. In the first term here, c prime is much smaller than the average value. Therefore, I can neglect c prime with respect to the average value. Okay. So, on the left side I will get r square u by d, okay, partial c bar by partial x. Okay. On the right side, c bar is an average concentration. It no longer depends upon r. Okay. It is independent of the radius. Okay. Therefore, the derivative of c bar with respect to radius will be 0. Okay. And all I am left with on the right side is 1 by r okay. So, this is the equation that I get. Okay. Therefore, I can solve this equation in order to find out what is c prime as a function of dc bar by dz. Okay. I can find out what is c prime as a function of partial of c bar with respect to partial z. Okay. Just integrate this equation, okay. Integrate it 2 times. Okay. First multiplied by r, integrate it once, then divide by r, and then integrate it a second time. Okay. If I do that, what I will get is, okay, it is an easy exercise to integrate it. Okay. What you will get is that r square u by 4 d, okay, into r star square minus r star power 4 by 4, okay, partial c bar by partial x, okay, plus some constant of integration is equal to c prime. Okay. That constant of integration can be determined from the condition that the average of c prime has to be equal to 0, because the average of the total concentration is already c bar. Okay. The average of the total concentration is already c bar. So, the average of c prime has to be equal to 0. Okay. So, if I apply the condition that average of c prime is equal to 0, okay, I can determine this unknown constant. Okay. It is quite an easy exercise. You will finally get that c prime is equal to r square u by 4 d, okay, into r star square minus r star power 4 by 2 minus 1 by 3, okay, partial c bar by partial x. Okay. You can easily verify that if I take this term here, multiply by r and integrate it from 0 to 1, this will end up being 0. Okay. So, that is the correction to the concentration field, okay, due to this additional, okay, due to this radial variation of the concentration. Okay. So, this is c prime of r star x, okay, the correction to the concentration field. Okay. What is the additional flux due to this correction to the concentration field? Okay. We know that the flux due to convection, okay, Jx due to convection, okay, is just equal to the velocity times the concentration. Okay. The flux, the local flux is equal to the velocity times the concentration. Okay. In this particular case, we are in a reference frame that is moving with the velocity u. Okay. We are in a reference frame that is moving with the velocity u. Okay. Therefore, in that case, the flux in a reference frame moving with the velocity u has to be equal to the local velocity minus the velocity u, okay, times the concentration. Okay. So, that is the flux in a reference frame moving with the velocity u. Okay. If you recall, I had said that we had taken a parabolic velocity profile. This is x, this is r. We have taken x prime is equal to x minus ut. Okay. and all of these derivatives that we had were all with respect to x prime. Okay. Okay. So, all of these were actually in a moving reference frame. Now, if I calculate the average of the flux, okay, if I calculate the average of the flux across the cross section, okay, the average flux J x across the cross section is equal to 2 integral 0 to 1 r dr, okay, times u x minus u into c. Okay. That is the average flux. Okay. Now, C can be separated into a cross sectional average concentration plus the radial dependent concentration. Okay. So, this can now be written as 2 integral 0 to 1 r star dr star u x minus u into c bar, okay, plus 2 integral 0 to 1 . Okay. So, that has two components, one is due to the radially averaged concentration and the other is due to the correction due to the fact that you have diffusion in the radial direction. This first term, okay, in this first term C bar is equal to is independent of R. Okay. So, this first term C bar is independent of R. Okay. Therefore, this just reduces to 2 C bar integral 0 to 1. Okay. Okay. And the second term is 2 integral 0 to 1 r dr u x minus u c prime. Okay. So, that is the second term. Okay. This first term has to average to 0 because I am taking the local velocity minus the cross sectional average velocity, integrating it over the cross section. Okay. That is what this first term is, because C bar was independent of radius, it came out of the integration. I am taking the local velocity minus the cross sectional average velocity and integrating it over the cross section. That has to obviously be 0, because the cross sectional average of the local velocity has to be equal to the average velocity. Okay. So, this term is equal to 0. This second term is in general non-zero because C prime does depend upon the radial location. Okay. So, this second term is in general non-zero. Okay. So, let us look at the second term. Okay. I told you that the flux, okay, J x bar is equal to 2 integral 0 to 1 r star dr star, okay, into u x minus u, okay, into C prime. Okay. U x was equal to 2 u into 1 minus r star square, parabolic velocity profile, which implies that u x minus u is equal to u into 1 minus 2 r star square. Okay. Equation for C prime we had just derived, okay, u r square by 48 d with a negative sign, okay, into partial C bar by partial x into r star square minus this we had just derived. Okay. So, therefore, what I have to do is to multiply these and then integrate. Okay. Therefore, J x bar, okay, I am sorry, this should be 4, okay, is equal to minus u r square by 4 d into partial C bar by partial x. Okay. Those are the two prefactors in this concentration. I have one prefactor in the velocity. Okay. So, I have to multiply that by u, okay, and then I have the radially dependent terms, okay, 2 integral 0 to 1 r dr, okay, times the radial part of the velocity 1 minus 2 r square into r square minus r power 4 by 4 minus 1 by 3. Okay. So, this integral has to be carried out. Okay. It is slightly complicated, but not too complicated. Okay. You can just multiply these two, integrate them, and quite easily you will get the result as minus u square r square, okay, by 4d partial c by partial x. Okay. I am sorry, 48 here. Okay. The constant turns out to be . Okay. So, this is the flux, the average flux, cross sectional average flux, okay, in the axial direction due to averaging over the flux in the radial direction, okay, due to carrying out an average of the flux in the radial direction. Okay. So, this flux has to be added to the convective flux. Okay. So, if I go back to my original equation, okay, if I go back to my original equation and do the cross sectional average, okay, I will get of course partial c bar by partial t, okay, plus the average convective flux, okay, u, okay, I am sorry, okay, is equal to minus u partial c by partial x, okay, that is the convective part, and then there is going to be a diffusive part, not diffusive but dispersive part, okay, due to this term here. Okay, this will be of the form minus partial j x by partial x. Okay. So, this is for the average concentration field. Okay. This represents the convection along with the mean velocity. This represents the dispersion about that mean location. Okay. This represents the dispersion about that mean location. Okay. So, I can write this as minus u partial c bar by partial x, okay, plus, okay, u square r square by 48 d partial square c bar by partial x square. Okay. I can rewrite this as partial c by partial t plus the average velocity partial c by partial x is equal to a dispersion coefficient times, okay, partial square c by partial x square. What is this dispersion coefficient? Okay. You can see from this term here, okay, the dispersion coefficient is equal to u square r square by 48 d. Okay. I can also write this as u r times Peclet number by 48, where the Peclet number is the radial Peclet number, okay, u r by d. Okay. So, this is the dispersion coefficient. Okay. Note that the dispersion coefficient has a diffusion coefficient in the denominator. Okay. So, as the diffusion coefficient decreases, as the system becomes molecularly less diffusive, the dispersion actually increases. Okay. As you make the system less diffusive, the dispersion in the axial direction actually increases. That is a counterintuitive result. The convection actually causes the dispersion to increase due to convective effects when diffusion coefficient decreases. Okay. So, this is the equation. Okay. If I write it again, partial c by partial t plus the mean velocity partial c by partial x. I should note that this expression is written for the cross sectional averaged velocity. Okay. So, this is of the form E partial square c by partial x square. Okay. And it represents the spreading, the dispersion, okay, of, okay, an element of solute, okay, the dispersion of an element of solute due to the mean flow which tends to distort it, okay, okay, which tends to distort this element of solute. Okay. Okay. where E was equal to u square r square by 48d. Okay. We had made two assumptions in this case. The first one was that streamwise diffusion is negligible. Okay. What that means is that the dispersion coefficient is much larger than the diffusion coefficient, the molecular diffusion coefficient, okay, or u square r square by 48d is much greater than 1 d, okay, which implies that Peclet number the whole square by 48. Okay. If I divide throughout by d, I will get u square r square by d square, which is the Peclet number square by 48 is much greater than 1. Okay. In this limit, when the Peclet number is large, the dispersion coefficient is much larger than the diffusion coefficient. In that case, okay, this analysis is valid. There is a second assumption which we had also made, that C prime is very much less than C bar. Okay. Now, we can examine the validity of that assumption. You know that C prime was equal to r square u by 4d partial C bar by partial x, okay, into r square minus r power 4 by 4 minus 1 by 3. Okay. So, this scales approximately as r square u by 4d partial C bar by partial x. Okay, that is C prime as a function of C bar. Okay. So, if the axial spread of this concentration field is some length L, okay, then C prime is approximately equal to r square u by 4d into C bar divided by L. Okay. And I can also write this as r u by 4d into r by L into C bar. Okay. It is equal to Peclet number by 4 r by L into C bar. Okay. So, this condition C prime is much smaller than C bar implies that, okay, Peclet number times r by L is actually much smaller than 1. Okay. Note that Peclet number is much larger than 1. Okay. The Peclet number itself is much larger than 1. The radius divided by the spread of this concentration field has to be much smaller than 1 in such a way that this product is much smaller than 1. In that case, I can assume that the radial variation of the concentration, okay, the radial variation of the concentration due to radial diffusion is much smaller than the average concentration itself. Okay. And in that limit, you find that the dispersion coefficient scales as u square r square by 48d. So, that is the paradoxical result of this Taylor dispersion problem. Okay. As the diffusion coefficient increases, the radial spread will decrease, the axial spread will decrease. Okay. As the diffusion coefficient decreases, the axial spread will increase. Okay. And that is because, okay, physically, I will try to give you a physical understanding of why that is so. Okay. If I have a film that was initially like this and it got deformed to something like this, okay, if radial diffusion was fast, okay, this would quickly spread in this direction, okay, and the concentration field would just look like something that looks like a constant concentration field. So, the concentration field would look something like that. Okay. So, radial diffusion would become equal to the spreading due to the axial flow very quickly. Whereas, if diffusion was small, okay, even when it distorts by a large amount, okay, even when it distorts by a large amount, the spreading will be relatively small, okay, on either side. Okay. If the spreading is relatively small on either side, then the axial dispersion is much larger, okay, because it distorts much larger if the spreading is much smaller on either side. Whereas, the spreading is large, okay, the distortion will be smaller, and due to that you get this dispersion coefficient. The effective diffusion due to the convective transport, okay, the dispersion coefficient as u square r square by 48d. It goes as inverse of the diffusion coefficient. Okay. This I have solved for you for a simple laminar flow problem, okay, where there is diffusion and a laminar flow, molecular diffusion significantly enhanced by convection, okay, resulting in dispersion. Similar things happen in turbulent flows. Okay. In turbulent flows you have fluctuating velocities. In those cases as well, as I showed you in one of our lectures in the beginning, there can be significant dispersion due to the fluid velocity fluctuations rather than due to the molecular velocity fluctuations. Okay. So, you could have significant dispersion because of convection, due to which the spreading is much faster than what you would expect simply on the basis of molecular diffusion. Okay. So, this causes a significant enhancement in the mass transport rates, just as boundary layers had caused a significant enhancement of the order of Peclet number to the half in the mass transfer rates. This actually causes an enhancement that goes as Peclet number square, okay, which is much faster in the axial dispersion itself. So, convection can have a significant effect on the mass transfer rates in the limit where convection is dominant compared to diffusion, because the concentration variations are limited to thin regions. Okay. In this case, that thin region is about the distorted initial plug. In the case of boundary layers, it is thin region is close to solid or liquid gas interfaces. These are all forced convection problems where the velocity field is specified for you and you have to solve the convection diffusion equation. In the remaining few lectures, we will look at what is called natural convection. That corresponds to, for example, convection close to heated surfaces. If I have a hot object in water or in air, the temperature in the fluid close to the object will be higher than that in the ambient fluid. Hotter fluid is lighter, and therefore, that hotter fluid will tend to rise. As the hotter fluid rises, colder fluid has to come in to compensate for the hotter fluid that has risen. That causes convection. That enhances transport rate much higher than what you would have just by conduction. That is a problem of what is called natural convection. The flow field itself is determined by the temperature field. Okay. So, there is no imposed velocity profile. Those natural convection problems, I will give you a brief introduction to you in the next few lectures. So, I will start natural convection in the next class. I will see you then.